So, hello student. In the series of the revision classes, today our chapter is work energy and power. In today's chapter, firstly I will discuss about some important topics of work energy and power. Then after that I will solve some previous year question of that chapter. Okay. Now the chapter name is work, energy and power. So firstly define work. What is work? So work is said to be done. Work is said to be done when a force applied on a body, when a force applied on a body displaces a body. Okay. So when you apply a force on a body and a body displaces, then it is said to be work done. If either of the those quantity was not present, neither force neither displacement, so there will not be a work done, or you can say a zero work done. Okay. Now come to next topic, that is work done by a constant force. Work done by a constant force. So case number one, when a force and displacement are in same direction. When force and displacement are in same direction. So what is the formula of work in that case? Are in same direction. Now see the condition. Suppose this is a body, and if I apply a force on that body, so what will happen? The body will displaces. The body will come to this position. Okay. After covering a distance as the body will come to this position. So what is the work done in that case? The work done is defined as force into displacement F into S. Now consider second case when force and displacement are inclined to an angle. Second case when force and displacement are inclined to an angle. When force and displacement are inclined to an angle. Inclined to each other at an angle theta. Now suppose that was a body. If you apply at an angle theta, if you apply a force at an angle theta, but the body displacement in that direction, so what do we have to take? We have to take that component of force which is known as F cos theta, which is in the displacement. Okay. So what is the work done in that case? So F cos theta into S. So on multiplying, you will get F S cos theta, or you can say it that F dot S. Okay. So work is also defined as the scalar product of defined as the scalar product of force and displacement. The scalar product of force and displacement. Force and displacement. Now come to its unit. What is the unit, SI unit of work? So SI unit of work is Newton meter or joule. Okay. Joule or comma Newton meter. And CGS unit is erg. And dimensional formula is force as dimensional formula mlt minus 2 and displacement as L. So dimensional formula will become ml2 t minus 2. Now the relation between its SI unit and its CS unit. So 1 joule is equal to 10 to the power 7 erg. Is the relation between joule and erg. Now come to next topic, that was types of work done. Next topic was types of work done. So there are three types of work done: positive work done, negative work done, and zero work done. So types of work done. There are three types of work done. First is positive work done. So what is positive work done? When both force and displacement are on the same direction, that work is known as the positive work. Okay. So work done is said to be positive. Work done is said to be positive when theta is positive. Okay. So theta is positive in, we know that the formula is fs cos theta, and the cos theta will positive in the first quadrant. So when theta is belongs to 0 to n degree, 0 to 90. Okay. For example, a positive work done are body falls freely under gravity. Body falls freely under gravity. And second example was horse pulled by a cart. Horse pull a cart. Now second was your negative work done. What is the negative work done? When theta is negative, so the work done will be negative. Negative work done. So what is negative work done? Work done is said to be negative when theta is belongs to 90 to 180. So work done is said to be negative, is said to be negative when theta is negative. When theta is negative, that means the theta belongs to 90 to 180 degree, 90 degree to 180 degree. That even in a second quadrant, beta, this is 0 to 90, not 90, and this is 90 to 180, means 90 not included. And in first one 0 included, 90 not included. In second one 90 not included, 180 included. Okay. So in the second quadrant cos theta is negative, so work done is negative. So in that case f is equal to minus of fs cos theta. Okay. So example of that are work done by frictional force. Work done by a frictional force. And second example was when a body is lifted upward, when a body is lifted upward, the work done by gravity is negative. The work done by gravity is negative. Now come to the last part, that was zero work done. So last was zero work done. When the work done is set to be zero, either f equal to 0, force equal to 0, or displacement equal to 0, or the angle between them is 90 degree. So in that case, the work done is said to be zero work done. So work done is said to be zero. Work done is said to be zero if either of the term is zero. If either f equal to 0, s equal to 0, or theta equal to 90 degree, because cos 90 is 0. Okay, so what are the example of zero work done? Earth moves around a circular path. Earth moves around a circular path. Second example was circular path. Motion around the sun. Motion of planets around the sun. Motion of planets around the sun. Next example was work done in pushing a immovable stone. In pushing a immovable stone. A immovable stone. So all that are the example of work, zero work done. And one more example is that when a coolie work, walks on a platform, so the force is applied downward and its direction is forward. So in that case, the angle between them is 90 degree. So in that case also the work done is zero. Now come to next one, when work done by a variable force. Variable force means when different forces given. So how you can find the work done? So work done by a variable force. If you have work done, if you have given variable force, then what you can do? Suppose that was the variable force, graph of the variable force. Now take 2 points. Suppose the first point is x1 and second point is x2. So work done is defined as integration of x1 to x2 f dx will be the formula of work done for variable force. Now come to next part, that was energy. So what is energy? Capacity of doing work or ability to doing work is known as energy. Okay. So what is energy? The capacity of doing work or ability to do work, ability to do work is known as energy. Is known as energy. It is a scalar quantity. It is a scalar quantity. Next one, dimensions and units are same. Dimensions and units are same as work done. Units are same as work done. That means its dimension is also mlt minus 2. ml to t minus 2. SI unit is joule. CGS unit is erg. So 1 joule equal to 10 to the power 7 erg will be the relation between joule and erg. Now come to next part. There are two types of energy. Many types of energy. By the way, mechanical energy, elastic energy, gravitational potential energy, and electrostatic energy. Many type of energy are there, but mainly we will discuss about the mechanical energy, and that in the mechanical energy our first part is the kinetic energy. So the first we will discuss about the kinetic energy. So what is kinetic energy, how the formula of kinetic energy will came, what is the relation of kinetic energy with work done. Then after that we will discuss about the potential energy. So firstly is our first topic is our kinetic energy. So it is defined as The energy possessed by the body as the energy possessed by the body by virtue of its motion, by virtue of its motion is known as kinetic energy. The formula of kinetic energy is half mv square. Okay. Now the example of the kinetic energy are turbine rotate due to kinetic energy. Turbine rotate due to kinetic energy. Rotate due to kinetic energy. Next, a bullet fire from a gun. A bullet fire from a gun can pierce a target, means break a target due to its kinetic energy. Next thing was windmills work on kinetic energy of air. So all that are the example of kinetic energy. Now come to the expression of kinetic energy. So I will prove the formula of kinetic energy by both method, by normal method, or you can say the algebraic method, or by the calculus method. So the first is the proof of kinetic energy. Expression of kinetic energy. Sorry, not proof. That was the expression. Expression for kinetic energy. So consider a body of mass m, initially at rest, initially at rest, it starts moving with velocity v. It starts moving with velocity v when a force F is applied. Now suppose that was the plane, and suppose that was a body having mass m. Now it is initially, its velocity is 0. Now if I apply the force, so what will happen? It will move. It will rotate, or it can move to some distance with velocity v. Okay. So it will move with some velocity v. So now apply the equation of motion, that v square minus u square equal to 2as. So v square minus u square is equal to 2as. Now here initial velocity is 0. So I will take 0 equal to 2as. Now v square equal to 2as. That means the s is equal to, sorry, a is equal to v square by 2s. So a equal to v square by 2s. Now the formula of work done is work done equal to force into displacement. Force is mass into acceleration into displacement, and acceleration is equal to v square by 2s into s. Now on cancelling, you will get half mv square, and this work done is converted into kinetic energy because it is associated with the moving body. So kinetic energy is equal to half of mv square. Now come with the next calculus method. Calculus method. Consider same condition, that when a body is initially at rest, and on applying the force, it will move with the velocity v. Okay, so the work done in moving a small distance dx is equal to f into dx. Now we know that f is equal to ma dx, and acceleration is change in velocity upon time. So dv by dt into dx. Now dx by dt change in displacement upon time. That was displacement, small displacement dx na. So dx by dt is equal to v. So mv dv equal to dw. Now integrate on both sides. Integrate on both sides. You will get integration dw equal to integration of mv dv. So when body is starting, when body is starting, so it's have initial velocity 0, and so initial velocity is 0, the work done is equal to 0. And when a body cover displacement dx, so at that time its velocity will be v and its work done will be w. So I can integrate this equation first within the limit of velocity 0 to v and a work done from 0 to w. So integration 0 to w dw equal to 0 to v dv. Okay, mv dv. So take an outside v dv 0 to v integration dw 0 to w. And we know that the formula of integration of x to the power n dx is x to the power n plus 1 upon n plus 1. Now come to the vdv. In that case we have power 1, so v1 plus 1 upon 1 plus 1 is equal to v square by 2. And integration dw, we can write integration dw as 1 into dw, or we can write 1 as w to the power 0 w. So if I apply formula, so w is 0 plus 1 upon 0 plus 1, so w will be the answer. Or you can simply say that the integration could differentiation, so you will get w. So w is from 0 to w, and m v square by 2 is from 0 to v. Now put upper limit and lower limit, so you will get w minus 0 is equal to m by 2 v square minus 0. So w equal to half m v square. And this work done is converted into kinetic energy because it is associated with moving body. So half mv square will be the formula of kinetic energy. Okay. Now come to the most important topic of that chapter, which was work energy theorem. That was very important for your exam point of view, its proof and its statement. Okay, so that was a very important topic. So what this theorem state? It states that work done by, according to this theorem, the work done by all forces is equal to change in kinetic energy, is equal to change in kinetic energy. So work done is equal to change in kinetic energy of the body. So what is kinetic energy? Change in kinetic energy. That means kinetic energy final minus kinetic energy initial will equal to work done. So what is that kinetic energy final minus kinetic energy initial? That means the change in kinetic energy is always equal to the work done in the kinetic energy. Okay. So that was important topic. And now comes to its expression or its proof. Now suppose a force acting on a body, force acting on a body of mass m, on a body of mass m produces an acceleration a, produces an acceleration a in time t after covering After covering after covering the distance s, the velocity changes the velocity changes from u to v, from u to v. So v square minus u square equal to 2as. In the same case, consider the previous example. Suppose that was the body. It was initially moving with initial velocity u. Now on applying force, it will move with increased velocity, that was v. Okay. So applying the equation of motion v square minus u square equal to 2s. So I will get the acceleration equal to v square minus u square by 2s. Now we know that work done is equal to force into displacement. Force is mass into acceleration into displacement. So in place of acceleration, I will put v square minus u square by 2s into s. So s will be cancelled. So half m v square minus half m u square. So work done equal to half m v square minus half m u square. So half mv square means kinetic energy final minus kinetic energy initial, which is equal to work done. That means change in kinetic energy is always equal to the work done on the body. Now come to the main part, that was the calculus part. If the only proof will came in the 3-number question, so that was very important. That will came, okay, by calculus method. The proof, the question come in the paper like that. The proof work energy theorem by the calculus method. So how you can prove by calculus method? So firstly, let dw be the small amount of work done, be the small amount of work done in moving a displacement dx, moving a displacement dx, then dw equal to force into ds. Now we know that force a formula m into a dx, and a is dv by dt. So dv by dt into dx. So dx by dt is velocity v. So mv dv equal to dw. Now integrate. When it is moving with initial, when it have initial velocity u, so work done equal to 0. And when it's move with the velocity v, so work done will be w. So integrate above equation within a limit of 0 to w, and here from u to v, v dv. Again integration v dv. I have proved it earlier that v dv equal to v square by 2. So v square by 2 u to v, and dw is only w, 0 to w. So on putting, we will get w minus 0 equal to half. Okay, m will also there. Half m v square minus u square. So work done equal to half m v square minus half m u square. Half m v square means kinetic energy final minus kinetic energy initial will equal to the work done. Okay. So that was the work energy theorem proved by the calculus method. Now come to the next part, that was relation between kinetic energy and momentum. And on the basis of that, you will get many questions in your examination or in your future examination. Means at a JEE point of view, this was also important. So relation between kinetic energy and momentum. So what is the relation between kinetic energy and momentum? We know that the kinetic energy formula is half mv square, and the momentum formula is m into v. So V equal to P by M. So on putting the value of V, you will get kinetic energy equal to half M P square by M square. So on cancelling one power, you will get Ke equal to 1 upon 2M P square. So relation between Ke and P is Ke equal to P square by 2M, or you can say that P square is equal to 2M Ke, or P is equal to under root 2M Ke. That was the relation. Okay, K square is K equal to P square by 2M, or P is equal to under root 2M Ke. Now the graph, first graph is when M is constant, sorry, when P is constant, when P is constant, so what will happen if P became constant? So K is inversely proportional to 2M, or you can directly say that K is inversely proportional to M. So K is inversely proportional to 2M. So the graph between Ke and M is inverse graph. That means it was like that. Now come to the next part. When K is constant. If K is constant, so P square is directly proportional to 2M. So P square is directly proportional to 2M. Now the graph between P and M was like that. And now come to third part. If M is constant, if M is constant, if M is constant, so K is directly proportional to P square. So the graph between K and P is, that was P, that was K. So the graph between K and P is, so remember these graph in your examination. Okay. Now come to the next part, that was your potential energy. Next topic is your potential energy. So what is the potential energy? The energy possessed by a body due to its virtue of its position or of its configuration. So the energy stored in a body, the energy stored in a body by virtue of its position or by its configuration. Configuration. Okay. So the example of potential energy are a body lying on the roof of a building, a body lying on the roof of a building, lying on the roof of a building. Next example was water stored on a dam. Water stored in a dam. Next example was due to P of stretched bow, the arrow goes forward. The arrow goes forward. So that was your potential energy. Now come to the next part, which was your gravitational potential energy. Gravitational potential energy. So what is the gravitational potential energy? So consider an object of mass mg taken to height h, taken to height h. Okay, suppose that was the surface. Okay, and it was taken to height h from the surface. It have mass m and acceleration due to gravity g. So work done is force into displacement. Force into displacement. So what is the force act on a body, which is equal to its weight mg, and the displacement is h. So mgh will be the work done, will be the potential energy. Okay, that work done is stored as a potential energy in a body. So u is equal to mgh, and at the surface of earth h is equal to 0, so potential energy becomes 0. Okay, now the relation between potential energy and with its kinetic energy. Okay, before it come to the main part, that was conservation force, or sorry, come to the main part, the law of conservation of energy. Law of conservation of energy. So law of conservation of energy, what it states, it states that energy can neither be created nor be destroyed. So according to this law, energy can neither be created nor be destroyed, can neither be created nor be destroyed, nor be destroyed. Only it can be transferred, only it can be transferred from one body to another body, transferred from one body to another body, from one body to another body. That means kinetic energy change to potential energy and potential energy change to kinetic energy, and the sum total of the change in kinetic energy, change in total energy will equal to 0. Okay, so change in total energy will also 0 because the t is constant, total energy is constant. So from that we will derive a relation between potential energy and work done. So the relation of PE with work done, PE with work done. We know that the total energy is 0. Change in total energy is 0 because total energy is constant. And according to work energy theorem, according to work energy theorem, WE theorem, the change in kinetic energy is equal to work done, or we can simply say that the change in kinetic energy is equal to work done. Okay, so that was the work energy theorem. Now what is delta TE? The total energy is the sum of the kinetic energy plus potential energy, and kinetic energy is equal to work done. So the delta PE equal to minus of delta KE. So delta PE equal to minus of work done. So always the potential energy is negative of work done by a body, or you can simply say that U is equal to negative of the work done. U is always negative of work done. Change in potential energy is always negative of work done. Now we know that work done is equal to force into displacement delta x. If delta x come in the by, so delta U by delta x is equal to minus F. Delta U by delta x, you can simply say that du by dx is equal to minus F, or F equal to minus du by dx. That means the change in potential, negative of change in potential energy with time is with displacement is equal to the force applied on a body. The negative of change in potential energy, negative of change in PE upon change in displacement. Okay, that was the relation between force and the potential energy. and the relation between work and potential energy is that. Okay, clear? Now come to one more the important topic that was also important for your exam point of view. Okay, this topic repeated 3 or 4 times in your examination. The of interconversion of Ke, interconversion of kinetic energy and potential energy during fall of a body, during fall of a body. That was also important for your exam point of view because this topic is repeated 3 to 4 times in your examination. So that was also important. So firstly, consider a ball, consider a ball of of mass m released from a height h, released from a height h, comes down, comes down towards comes downward due to gravity with increasing velocity, with increasing velocity. So that was a body which was taken at height h from the surface of earth. It have mass m. Initially its velocity is 0 and the final velocity we did not know. So at initially its potential energy is mgh and its kinetic energy is half mv square. Okay, now consider the motion of a ball when a body is falling. So what will happen? What will its final velocity? V square. V square minus u square equal to 2as. We know that here u is 0. So v square minus 0 whole square equal to 2gh. Here acceleration due to gravity is acts downward and bodies moves downward. Okay, so we will take its positive. So v square is equal to 2gh. So the value of v square is 2gh. So in place of v square, I am putting 2gh. So 2 is cancelled by 2 equal to mgh. Kinetic energy is equal to mgh. And what is mgh? Potential energy. So when a body falls from a certain height, so its kinetic energy will changing to potential energy, or you can say that its potential energy changed to kinetic energy, but the total energy remain constant. Now come to next topic. That was your conservative force and non-conservative force. Conservative force and second one is non-conservative force. Non-conservative force. So firstly, what is conservative force? The force is by which work done depends only on initial and final position of a body. Initial and final position of a body, but it does not depend It does not depend on path. So that type of forces are called conservative force. Are called conservative force. Conservative force. So the example of conservative force are gravitational force, gravitational force, or elastic force on spring. Elastic force on string. So both are the example of conservative force. Means that did not depend on the part. It was depend on only initial and final position. And non-conservative force are the force which depend on the path simply. So the work done, those forces in which work depend on the path. Work depend on the path are known as non-conservative force. So the example of non-conservative force are frictional force. Frictional force depend on the path. So come to the one more important topic, conservation of mechanical energy in a freely falling body. When a body falls freely, so what is the so it follows the conservation of energy at any point or not. So that was the conservation of mechanical energy in the freely falling body. So that topic was very much important for your exam points of view because it have come in your previous year. Okay, I think 2 or 3 times. Conservative conservation of mechanical energy, conservation of mechanical energy in freely falling body, in freely falling body. So what is the conservation of mechanical energy in the freely falling body? Now consider the condition here. What is the condition? That consider a body of mass m, consider a body of mass m lying at position A, lying at position A at height h above the ground, at height h above the ground. As the body falls, its kinetic energy increases. As body falls, its kinetic energy increases and potential energy decreases. Potential energy decreases. So, if I draw the diagram, suppose that was position A at where body remains. Now, a body is falling down. Wait 1 minute. Huh? Suppose that a body at point A, it's have kinetic energy 0, and at point C, it have potential energy 0. Now, suppose at B, the height between A and C, the distance between A and C is h, means the height of A. Now, suppose A to B is x. So, what is B to C? H minus x. H minus x. Now, at point A, at point A, body is at rest. So at point A, body is at rest. So what will happen if the body is at rest? So it's means its velocity is zero, and if its velocity is zero, so kinetic energy is zero. Only at that case it have potential energy mgh. So total energy, or you can say that total mechanical energy at point A will be total mechanical energy at point A is equal to Ke at that point and Pe at that point. Kinetic energy is zero at that point and potential energy is mgh at that point. Okay. So the total kinetic energy, total mechanical energy will become mgh. Now at point B, at point B, so at point B, the potential energy will be, here the void will be h minus x. So the potential energy will become mg h minus x, and the velocity will become v square minus u square equal to 2as. We know that initial velocity is 0, so v square minus 0 equal to 2g, and at B point it was come from that, so the distance will be x. Okay, so v square equal to 2gx. So the kinetic energy of the body is half mv square, and we know that v square equal to 2gx. 2gx, so that was cancelled. So mgx will be the kinetic energy of a body. Now the total energy is sum of the potential energy plus kinetic energy. So the potential energy is mg h minus x plus mgx. Now if you take mg common, so you will get h minus x plus x. So mgh will be the total energy at point B, which is same at point A. Now come to the last point, at point C. That means at a ground. So at a ground, its height became zero because it come at that position. So at the surface of the earth, the kinetic potential energy is zero, and for kinetic energy, v square minus u square is equal to 2as. U is zero, so v square equal to 2gh. So at point C, v is equal to under root 2 v square equal to 2gh. That is at point B. Okay, so at point C, the potential energy is zero and the kinetic energy is half mv square, and v square equal to 2gh, so half m into 2gh, so that was cancelled. So mgh, so the total mechanical energy at point C is also the sum of potential energy and kinetic energy. So the total mechanical energy will be the sum of kinetic energy plus potential energy. So the kinetic energy is mgh at that point and potential energy is zero. So the total mechanical energy is also mgh. So that was the law of conservation of energy that we have seen, that at point A, at point B, and at point C all have the same value of total mechanical energy, which is equal to mgh. So that follows the law of conservation of energy, that energy can be neither be created nor be destroyed. Only it can be transferred from one form to another form. So we have seen in that example that the energy will be transferred from kinetic energy to potential energy and potential energy to kinetic energy, but the total energy remain constant, which is equal to the mgh of the body. Okay, so that's all for today class. So if you have doubt in any topic or in any question, so you will send that doubt or topic to sir or ma'am. They will forward me and I will solve that part in video. Okay, that's all for today. Thank you everyone. In the next part I will discuss some other topics of kinetic of that chapter, and important question that comes in your previous year and some numerical. Okay, so that's all for today. Thank you everyone.